We have been solving for magnetic field due to current distributions. And one problem that I solved in the previous lecture was Jackson 5.2 A part, where we showed that if I have a long solenoid in which the current is flowing in the tangential or phi direction, then the field inside is equal to mu naught n I, where n equals number of turns per unit length, and I is the current. And outside B is 0. This we showed by explicit calculation. So, this was an explicit calculation. Based on Biot-Savart law. Today, I want to do part B of it, because this will bring out all the subtleties and all the mathematical tools that we are going to use. So, this will bring out all that, how we use that in solving for a magnetic field. So, what part B says? So, this is 5.2 B from Jackson's book. It is talking about a realistic solenoid long realistic solenoid, and by realistic one means that the turns are actually at an angle. So, they go like this and they come back like this. The current is going up like this, and this is at an angle theta. If I make it slightly bigger, so the current is going like this, and let me make the next turn a little farther off. This distance is known as the pitch. So, by the time this takes one turn, the turn has moved up by distance p. The angle, as I said, with the z axis with the horizontal axis is theta, and what we want to show is that the field inside is still mu naught n I, and field outside is not equal to 0. Rather, the field outside, and we smoothed it, kind of it's averaged over, or the coils, the turns are very close. So, that field is roughly smooth outside. We will later comment on what close turns means. Outside is as if there is a current I flowing along the axis of the solenoid. That is, the field outside B, just outside, is equal to mu naught I over 2 pi times the radius, let us say this is I, in the phi direction. This is what we want to show. So, we will first give a physical argument as to why this happens, and then we will derive it mathematically using Biot-Savart law. So, let us do that. So, first the physical argument. So, here is the solenoid, and we are saying that these turns are very close, and here I am making it slightly farther apart to give the geometry. Then I can think of the current as having a surface current density in the direction shown by this red arrow. This is the surface current density K. What will be the value of the surface current density? Let us find that out. So, current is I, and this is spread over a distance, which I am going to show now with this green color here. This is pitch P. So, perpendicular distance this is theta, because this angle is theta. So, this distance, perpendicular distance, the perpendicular cross section over which, or length over which the current is flowing, is P cosine of theta. Therefore, the current density K is equal to I over P cosine of theta in the direction shown. Now, this current density has two components. This has a horizontal component and this has a vertical component. So, I can think of this solenoid as if there is a surface current K going like this, and there is a surface current going up. This is K over P cosine of theta, and this is K over P cosine of theta is the K, the vertical component. So, let us write this here. K vertical is going to be I over P cosine of theta times sine of theta, which is going to be I over P tangent of theta. And so, this is not correct, this is K over P tangent of theta, and K horizontal is going to be K over P cosine theta times cosine theta. So, that is I over P. Even that is not correct, what I have written earlier, it is I over P tangent of theta. This is K. Now, the current which is vertical is going to be K vertical times 2 pi A, where A is the radius. So, this is going to be I over P times 2 pi A tangent of theta. So, what we have found is, given the solenoid, there is this K surface current in the direction shown, and this has a K horizontal and a K vertical. K horizontal is I over P and K vertical is I over P tangent theta, and therefore, the surface current moving up the solenoid is equal to K vertical times 2 pi A, which is I over p times 2 pi a tangent of theta. What is tangent of theta? Look at this. This angle is theta. So, by the time two pi a distance is travelled, the wire moves up by p. That is, by the time I travel this distance 2 pi a, this is the distance, vertical distance travelled, and this angle is theta. So, tangent theta is p over 2 pi a, and this immediately gives you I vertical is equal to I over p times 2 pi a times p over 2 pi a. This cancels, is equal to I, and therefore, by Ampere's law, B outside will be mu 0 over 2 pi a I phi. So, we have seen that in a realistic solenoid there will be a field outside. I will leave for you to think about the field inside, which is in z direction. Now, let us calculate the same thing using Biot-Savart law. Applying Biot-Savart law. So, in applying Biot-Savart law, how would I calculate B? I would calculate B at some point r as integral dl prime cross r minus r prime over r minus r prime cubed mu 0 I over 4 pi, and I need to calculate this integral. Is to be calculated for the turning wire. Here it is. Here is the turning wire. And it makes a one turn to 2 pi and then moves up again. So, what I will do is calculate the field due to one turn, and then integrate over all turns, which basically means integrate over z or z prime. I'll tell you what it is. So, let's see what is dl prime. Let me make this solenoid again. Here is this wire. Since solenoid is infinitely long, the field is independent of z. That is where on the z axis I am calculating, it does not matter. So, for convenience, we take z to be 0. So, the r point is equal to some s in cylindrical coordinates, small s 0, and r prime is going to be some s prime at z prime. dl prime is along the wire. So, along the wire has dl prime is equal to 1. When it turns, it is going to move in the phi direction. So, that is going to be a times d phi prime, a is the radius, in the phi prime direction, plus is going to move in the z direction. So, that is going to be d z prime in the z direction. We have already seen that z prime is equal to p over 2 pi a times phi prime a, because by the time phi prime becomes 2 pi, z prime moves up by a. This implies that d z prime is going to be equal to p over 2 pi times d phi prime, and therefore, I can write d l prime is equal to a d phi prime in the phi prime direction plus d z prime we have just determined is p over 2 pi d phi prime in the z direction, which I can write as a d phi prime plus p over 2 pi a in the z direction. Z and z prime does not really matter. So, what we are calculating is b at sum s 0 is equal to mu 0 I over 4 pi integration 0 to 2 pi a d phi prime plus p over 2 pi a z cross r minus r prime, which is going to be s minus s prime plus z, we have taken that to be 0, minus z prime in the z direction, divided by this r minus r prime cubed. That is the definition. Probably I missed that term in the previous slide. Oh, I have it. This is what we are calculating. So, let us find out. Just to recap, what I am doing is, here is the solenoid, here is z equals 0, I am at a point z prime somewhere, and this is my d l prime. And if I look at it from the top, I am calculating the field at some point s, it could be outside or inside, and my d l is somewhere here. This direction is s prime, and the direction shown by red is phi prime, and z is coming up. So, now that I have given you a geometric picture, we can calculate the cross product easily. Cross product I am calculating is phi prime plus p over 2 pi a z cross s minus s prime minus z prime z, which is going to be equal to phi prime cross s. Magnitude of s is s, phi prime cross s. So, let us see. This is s vector, this is s prime vector. Let us say this is at angle phi, s prime is at angle phi prime. So, that the angle between s and s prime is phi minus phi prime. So, let us make it again s prime s, this angle is phi prime minus phi, and perpendicular to s prime is phi prime. So, the angle between phi prime and s is pi by 2 minus phi prime minus phi. So, I will go back to the calculation here on top. So, this is s sine of pi by 2 minus phi prime minus phi, and this is going to be in phi prime cross s, you can see is going to be in the minus z direction. Minus phi prime cross unit vector s prime, and the distance is a. So, I can replace this by a z. Phi prime cross s prime is minus z. Then I have minus z prime, and phi prime cross z is going to be s prime unit vector. Then I have the next term, which is p s over 2 pi a z cross s, and z cross s is going to be in the phi direction. Not phi prime, but phi direction. Minus p a over 2 pi a z cross s prime, which is going to be in the phi prime direction, and z cross z is 0. So, these are the terms that I have. These are the cross terms that I have, which now I can write as equal to s cosine of phi with a minus sign plus a z unit vector minus z prime s prime unit vector plus p over 2 pi a. Inside I am going to have s phi minus a phi prime vector. Now, I am ready to do the calculation. So, I will write now b due to one loop is equal to mu naught I over 4 pi integration a d phi prime, and then all that I had from the previous slide minus s cosine phi prime minus phi. I hope I had that. Okay, so, let me correct that. It was phi prime minus phi plus a in the z direction minus z prime in the s prime direction, and then I have plus p over 2 pi a s phi minus a phi prime closed divided by s minus s prime mod square plus z prime square raised to 3 by 2. This is what I should be calculating, and then once I have gotten this, the net B total at R will be given by this B R that I have written above, d z prime from minus infinity to plus infinity. That will be my answer. Looking at the total answer, I can immediately drop out one term. Notice the term, notice that the term proportional to S prime unit vector has Z prime over S minus S prime square plus Z prime square dz prime, and this will be 0 because the integrand is odd in Z prime. Therefore, that term can be dropped. So, now I have only two terms to be evaluated. Let us first calculate the Z component of the field. So, calculate the Z component. Z component is going to be, so Bz, B total Z component at R is going to be mu naught I over 4 pi integration a d phi prime. Then I have inside a minus s cosine of phi prime minus phi divided by s vector minus s prime vector square plus z prime square raised to 3 by 2, and there is a dz prime here, minus infinity to infinity. Phi prime is 0 to 2 pi. This is the integral I need to calculate. I will now use the symmetry of the problem and say that since field is independent of phi because of cylindrical symmetry, take phi equal to 0, then phi prime, phi unit vector will be in the y direction. Then I can revert back to it later. So, it does not matter where I calculate, just taking phi equals 0 makes life easy, and therefore, B total Z at R is going to be equal to mu 0 I over 4 pi a d phi prime 0 to 2 pi integration minus infinity to infinity dz prime. Then I have a minus s cosine of phi prime, because phi I have taken to be 0, divided by mod s is now at phi equals 0 minus s prime square plus z prime square raised to 3 by 2. So, let us first perform z prime integral. The z prime integral is straightforward, dz prime over s minus s prime square plus z prime square raised to 3 by 2 minus infinity to infinity is going to be equal to, I will leave it for you to do it. You will find that this comes out to be 2 over s minus s prime mod square. Well, let me also remind you here, when doing z prime integral, I should take n times dz prime, because in the distance dz prime there are n times dz prime terms. So, that factor of n I will take into account. So, I should put it right here. Let me put an n here also on the left hand side of the screen. I put it in green here. Now, I can expand this. So, 2 over mod s minus s prime square is nothing but 2 divided by s square plus a square minus 2 a s cosine of phi prime. raised to, that is it, there is no power, there is square itself, because S prime vector is A S prime unit vector, and angle between S unit vector and S prime unit vector, S I am taking to be x, is nothing but phi prime. And therefore, I get B z total R vector is equal to mu naught I n over 4 pi integration 0 to 2 pi A d phi prime times A minus S cosine phi prime divided by S square plus A square minus 2 A s cosine phi prime, and there is a factor of 2 also here somewhere. 2. This is an easy integral to calculate. So, let us now look at the integral. Integration d phi prime is out here somewhere 0 to 2 pi A minus S cosine phi prime divided by S square plus A square minus 2 A s cosine phi prime. This term occurs, okay, this term occurs in calculating electric field due to a uniform surface charge density carrying cylindrical shell. And the cylindrical shell will be of radius S, and the field is calculated at distance A. Let me explain that how. So, here I have a cylinder of radius S, and I want to calculate the field at a distance A. Right. So, let us look at it from the top. So, what I will do is at angle phi, I will take this thin line, here is that thin line at angle phi, and calculate the field at a distance A. This is S. The field due to this thin line at this point is going to be in the direction shown. And because of the symmetry, only the horizontal component will survive. So, only this component matters. And I know if I calculate the total field due to this is nothing but lambda over 2 pi epsilon 0 A. That much I know, but if I calculate it through the integral, let us see how much will it come out to be. The distance from that line to the point is S square plus A square minus 2 A s cosine phi square root. This angle is phi, this is d phi, not phi. And the horizontal component therefore is going to be is that E due to whatever that thing is times cosine of theta, which is going to be A minus S cosine of phi divided by square root of S square plus A square minus 2 A S cosine of phi. So, you see this factor is coming right here. So, we can therefore calculate this integral. Let us see now do the detailed calculation. So, what I am calculating is I have this cylindrical shell. Let us say now it carries charge sigma per unit area. Therefore, for this small length S d phi, I am going to have the charge per unit length as sigma S d phi, then the field at this distance A E is going to be sigma S d phi over 2 pi epsilon 0 square root of S square plus A square minus 2 A S cosine of phi, and E horizontal, we have already calculated that cosine, is going to be sigma S d phi over 2 pi epsilon 0 A minus S cosine phi divided by S square plus A square minus 2 A S cosine of phi. Total field is going to be therefore sigma S over 2 pi epsilon 0 integration 0 to 2 pi d phi A minus S cosine phi divided by S square plus A square minus 2 A S cosine of phi. And this I know is equal to lambda over 2 pi epsilon 0 A. Lambda is 2 pi A sigma divided by 2 pi epsilon 0 A. It's 2 pi cancels, A cancels. Oh, sorry, this is incorrect. Lambda is 2 pi S. S is the radius of the shell times sigma divided by 2 pi epsilon 0 A. And now I can cancel this 2 pi and 2 pi. So, this comes out to be S sigma over epsilon 0 A. So, sigma S over 2 pi epsilon 0 0 to 2 pi d phi A minus S cosine phi over S square plus A square minus 2 A S cosine of phi is equal to S sigma over epsilon 0 A. Again sigma S cancel, so do epsilon 0, and this gives me A d phi 0 to 2 pi A minus S cosine phi divided by S square plus A square minus 2 A S cosine phi is equal to 2 pi. Or I can even erase this A from here and put this as 2 pi over A. That is the answer. So, I can now take this integral and put it in my original expression. So, this is a useful way of getting the value of an integral. I explicitly wrote the integral and also related it to the answer obtained by Gauss's law, equated the two and got my answer. So, let us see now what does B z come out to be. So, expression for B z total was mu 0 I n divided by 4 pi integration a d phi prime a minus s cosine phi prime divided by s square plus a square minus 2 a s cosine phi prime, and there was a factor of 2 here. So, this now from the integral that we have calculated is mu 0 I n over 4 pi a 2 a times 2 pi by a cancels, 4 pi cancels, and you get mu 0 I n. Now, this is for inside the cylinder. How do we know that? You see, this integral that we calculated was related to electric field for this cylindrical shell of radius s. So, this was E is not 0 for a greater than s, and E is 0 for a less than s. Let us write it explicitly. E is 0 inside and E is lambda over 2 pi epsilon 0 s or a outside. So, this is for a greater than s, and this is will be 0 for a less than s. What does it mean? So, when I have this solenoid, there is a z component of the field B z, which is mu naught n I, because inside I have s less than a or a greater than s, and B z is 0 outside, because here I have a less than s or s greater than a. So, we have calculated B z is what this is given here, mu naught n I inside and 0 outside. What about other components? Now, we will calculate the other components. For the other components, recall that I have the only one expression left, and that is B, the other component other than z, is equal to mu naught n I over 4 pi, then I had a p over 2 pi, there is some other expression, and then I had integral 0 to 2 pi d phi prime s phi minus a phi prime divided by mod s minus s prime square plus z prime square raised to 3 by 2, and there will be a dz prime, and dz prime will be from minus infinity to infinity. The other term had dropped out. So, now I got to evaluate this. So, I will just focus on this integral here. Again, as I do the z prime integral, dz prime from minus infinity to infinity divided by mod s minus s prime square plus z prime square raised to 3 by 2. This gives me, we have already done this, divided by s minus s prime whole square. So, I am left with B equals mu 0 n I over 4 pi p over 2 pi times integral 0 to 2 pi. Just keep checking the expressions I have, because I may have missed something here. S phi minus a phi prime divided by mod s minus s prime whole square. Now, I have taken phi to be 0, implies that phi is equal to y. Keep that in mind. And phi prime unit vector would be minus sin phi prime x plus cosine phi prime y. And therefore, B is going to be mu 0 n I p over 4 pi times 2 pi, keeping the whole thing together, integration 0 to 2 pi d phi prime s minus a cosine phi prime divided by s square plus a square minus 2 a s cosine phi prime in the y direction, and plus mu 0 n I p over 4 pi times 2 pi integration 0 to 2 pi d phi prime sin phi prime over s square plus a square minus 2 a s cosine phi prime. You can easily show, and this will be in the x direction, you can easily show that this integral is 0. And the other integral, this one, is similar to the earlier integral. With a and s interchange. That means, what it is showing is the electric field by a shell, cylindrical shell carrying uniform charge of radius a at a distance s. And therefore, the integral, if I write it as I will be 0 inside and I will be 2 pi over s outside. And therefore, this field is in y direction, which is nothing but phi direction if I take angle to be phi, and you can calculate the rest. Keep in mind that n times p will give you, see, n is 1 over p. So, it will give me 1. Okay. So, I will leave the rest of the calculation for you, and you can show how this gives the field as if the current is flowing in the z direction on the shell, uniformly distributed, and this B inside will be 0. So, what we see is that B inside will be 0 in the horizontal direction, and vertical direction it will be mu naught n I, and outside it will be like that of a wire carrying current I along the axis of the cylinder. I am leaving the rest of the calculation for you. So, I will now conclude this by saying that we have solved problem 5.2b of Jackson in a mathematically rigorous way. Along the way, we also learned how to evaluate some integrals by recognizing that they occur in calculation of electric field of some symmetric systems. And I have left part of the problem is left for you to complete. Thank you.